sandwich theorem or squeeze theorem. This is the most important theorem for your semester exams. If you want to learn this, you must and should watch my previous videos. Then it is easy to understand. Okay. Next, this is also a named theorem, right? Sandwich theorem. So you must and should read theorem statement along with the proof. See here, what is our statement here? If sequence Sn, sequence Tn and sequence Un are three sequences such that first condition Sn less than or equals to Un less than or equals to Tn for n greater than or equals to k, where k is some positive integer. And second condition, limit Sn is equals to limit Tn is equals to L. Then we need to prove limit Un is equals to L. See here, first they consider three sequences. What are the sequences? Sequence Sn, sequence Tn and sequence Un. These are our three sequences. So first we need to consider these three sequences. Finally, what we need to prove here? Limit Un is equals to L by using these these two conditions. So we need to suppose first condition, second condition. Okay. What is our first condition? Say here, Sn less than or equals to Un less than or equals to Tn for n greater than or equals to k, where k is some positive integer. Sn, Un, Tn are nothing but nth terms of sequence Sn, sequence Tn and sequence Un. See here, Sn is the nth term of sequence Sn, Un is the nth term of sequence Un, Tn is the nth term of sequence Tn. These are the nth terms of these three sequences. For n greater than or equals to k, k is a positive integers. Positive integer is nothing but 1 to infinity. Next, what is our second condition? See here, limit Sn is equals to L and limit Tn is equals to L. So we can use this condition also. Finally, what we need to prove here? Limit Un is equals to L. Limit Un is equals to L. We know the definition of limit of a sequence. What is the limit of a sequence definition? For any epsilon greater than 0, there exists a positive integer such that mod Un minus L less than epsilon for all epsilon for all n greater than or equals to, what is our positive integer here? M. Okay. This is a condition for limit of a sequence. If we prove this condition, then we can write limit Un is equals to L. This is the definition of limit of a sequence. This is the definition of limit of a sequence. What is the condition here? See here, for any epsilon greater than 0. So we need to consider an epsilon first. There exists a m belongs to z plus such that what we need to prove here? Mod Un minus L less than epsilon for all n greater than or equals to m. If we prove this condition, then we can write from this limit Un is equals to L. Similarly, what we need to prove here? Limit Un is equals to L. So for this we need to prove this type of condition. Okay. So for this we need to consider first epsilon greater than 0. So let epsilon greater than 0. First I am considering three sequences. Let sequence Sn, sequence Tn and sequence Un be three sequences Next, what we need to suppose here? There are two conditions, right? So we need to suppose these two conditions. Suppose Sn less than or equals to Un less than or equals to Tn for n greater than or equals to K. K is some positive integer. So we can write K belongs to Z plus. We can write, right? K belongs to Z plus. Next, we need to suppose one more condition. What is that condition? See here. Limit Sn is equals to L, which is equals to limit Tn is equals to L. So limit Sn is equals to L, which is equals to limit Tn. Limit Sn value, limit Tn value, same. Okay. By using these two conditions, finally we need to prove limit Un is equals to L. Claim is nothing but limit Un is equals to L. For this we need to prove one condition. What is that condition? For any epsilon greater than 0, there exists some positive integer such that mod Un minus L less than epsilon for all n greater than or equals to m. This is the condition we need to prove. Okay, see here. What we have here, limit Sn is equals to L. Since limit Sn is equals to L. Again, by the definition of a limit of a sequence, by the definition of limit of a sequence, this is we can write for any epsilon greater than 0, there exists positive integer and then belongs to Z plus such that mod Sn minus L less than epsilon for all n greater than or equals to m1. By the definition of limit of a sequence, from this condition we can write this condition. Okay. See here, for any epsilon greater than 0, there exists a positive integer. What is the positive integer here? m1, such that it should satisfy this type of condition. Mod Sn minus L less than epsilon. So we have this condition right now. Mod Sn minus L less than epsilon. By the modulus condition we can write minus epsilon less than Sn minus L less than plus epsilon. Add L throughout the inequality. What we have here? L minus epsilon less than Sn minus L plus L. L plus epsilon. Minus L plus L will get cancelled. We remain with L minus epsilon less than Sn less than L plus epsilon. Consider this as equation 1. Okay. Next we have one more condition. What we used here, limit Sn is equals to L. Another condition is limit Tn is equals to L. So again, by the definition of a limit of a sequence, we can write also we have limit Tn is equals to L, again by the condition 2. So again by the definition of limit of a sequence, by the definition of limit of a sequence we can write for any epsilon greater than 0, there exists a positive integer m2 belongs to Z plus such that mod Tn, what is our nth term here? Tn. So Tn minus L less than epsilon for all n greater than or equals to m2. Again what we used here? limit of a sequence definition. So for these definitions you must and should watch my previous videos. Then it is easy to understand. Okay. Next, see here. What is the definition here? Limit of a sequence. From this we can write limit Tn minus L less than epsilon. Again by the modulus condition, what we need to write here? Minus epsilon less than Tn minus epsilon less than plus epsilon. Again throughout the inequality add L minus epsilon, L plus Tn minus L plus epsilon. L will get cancelled. We remain with L minus epsilon Tn less than L plus epsilon. This is our second equation. Consider this as second equation. From equation 1 and 2, we can solve limit un is equals to, we need to prove limit un is equals to L. Okay. Okay, now we have two conditions from equation 1 and 2. What are the conditions here? L minus epsilon less than Sn less than L plus epsilon for all n greater than or equals to m1. Next, L minus epsilon less than Tn less than L plus epsilon for all n greater than or equals to m2. These are our two conditions from supposition 2. What is our supposition 1? By supposition 1, we have Sn less than or equals to Tn un less than or equals to Tn for all n greater than or equals to k, where k is a positive integer. See here, n greater than or equals to m1, n greater than or equals to m2 and n greater than or equals to k. m1, m2, k are positive integers. So from these three positive integers we can consider one m that should be equal to maximum of m1, m2, k. Clear? See here, n is the greatest one among m1. Similarly, n is greater than or equals to m2. N is also greater than or equals to k. So from these three conditions, I am considering one m that is equals to maximum of m1, m2, k. Okay. So in place of m1 we can write m. Similarly in place of m2 we can write m. Similarly in place of k also we can write m. So from these three conditions now we have L minus epsilon less than Sn less than L plus epsilon for all n greater than or equals to m. Next, and L minus epsilon less than Tn less than L plus epsilon less than for all n greater than or equals to m. Similarly, from this condition we can write also Sn less than or equals to un less than or equals to Tn for all n greater than or equals to m. See here. Next, by using this condition, I want to prove limit un is equals to L. Okay. Now, Sn less than or equals to un less than or equals to Tn. See here, L minus epsilon less than Sn for all n greater than or equals to, what do you have here? For all n greater than or equals to m. What do you have here? N greater than or equals to m. Also L minus epsilon less than Sn. So from this we can write L minus epsilon less than Sn, which is less than or equals to un, less than or equals to Tn. Tn also less than L plus epsilon. All these conditions are existed from n greater for all n greater than or equals to m. So for all n greater than or equals to m. See here, for example, 2 less than 3, 3 less than 4, 4 less than 5, 5 less than 6. So from this we can write 2 less than 4 less than 6. From this we can write like this, right? Similarly, 2 2 always less than 3. Similarly, 2 always less than 4. Same condition, see here. From this condition, we can write L minus epsilon less than or equals to Un. L minus epsilon less than Sn. So, L minus epsilon also less than or equals to Un. Similarly, Un less than or equals to Tn. Tn always less than L plus epsilon. So, from this we can write Un less than or equals to L plus epsilon for all n greater than or equals to m. Subtract L throughout the inequality. Plus L minus L get cancelled. We remain with minus epsilon less than or equals to Un minus L less than or equals to epsilon for all n greater than or equals to m. Again by the modularity condition, what do you have here? Un minus L less than epsilon for all n greater than or equals to m. Is m is positive integer? Yes, right? Why? Because m is the maximum of m1, m2, k. m1 positive integer, m2 positive integer, k positive integer. So from this we can write m is also a positive integer. First, what we considered? For any epsilon greater than 0, there exists a positive integer. Is m positive integer? M positive integer. M positive integer. There exists a positive integer m such that finally what we proved here? Un minus L less than epsilon for all n greater than equals to m. This is our condition. This is the definition of limit of a sequence. So by this we can write limit Un is equals to L. This is the condition we need to prove, right? Okay, this is the condition we need to prove. What we considered first? First we considered 3 sequences. Sequence Sn, sequence Tn, sequence Un. Next, we need to suppose 2 more conditions. What are the conditions? Sn less than or equals to Un less than or equals to Tn. This is our first condition. Next condition, limit Sn is equals to L and limit Tn is equals to L. This is our 2 suppositions. By using these 2 suppositions, we need to prove limit Un is equals to L. We need to prove this condition by using which definition? By the definition of limit of a sequence. From this theorem, you need to learn limit of a sequence definition. Without that, you can't understand it. Okay? This is a sandwich theorem proof. Next class, I will explain about problems based on sandwich theorem. Okay? Do like, share and subscribe my channel. Thank you.